and today our topic is linear algebra using SageMath. I welcome you, sir, to this session. Participants, if you are having any doubt, first you can clear that doubt and then we can start the today's session. Okay, sir?
Yes, yes.
Okay. Welcome you, sir, to the session to hand over.
Thank you, and good afternoon to everybody. So I hope that the discussions that we had in the last two sessions were somewhat comfortable to all of you. And the basic things that we were discussed in we were discussing in the last two sessions were from mainly from number theory, and after that from calculus. Now probably we will be discussing linear algebra, and together with that a little bit of vector calculus also, because these two things most of the times go together. So our main focus will be on linear algebra and some vector calculus. We will also see that the plotting commands that we discussed in the last session, how can those things be used for plotting vectors. So if there is any question regarding the last two sessions, you may please ask me, and after that I will start. If there are no questions, I'm starting now. So,
Okay, sir, we can start.
okay. We know that in linear algebra, many of the computations are based on representations of vectors, etc., in matrix form. So, even in linear algebra, row and columns are always treated as vectors. So, we need to understand how to represent a vector in SageMath first. Representing a vector in SageMath is very easy. The only thing is that you have to write down, you have to denote the vector as a list. A list means that it's a comma separated numbers enclosed in two square brackets, and then use the command vector, and then the variable to which you are assigning it will become a vector. So the commands are the following. Suppose that I want to define a vector. Suppose that I want to define the vector v equal to 2i plus 3j plus 4k. Suppose that this is the vector that I want to define. See, whatever line I am starting with this hash symbol, they are known as comments, and these lines will not make any impact in the code that I am typing below. So this is just for our information. This command has no effect. If you're typing or not typing, that is not going to make any impact. This is only for the information that what I am going to do. So I'm defining v equal to vector. So this is the command, and we have to enclose whatever we are going to type inside two open close brackets. Now the vector has to be enclosed in a square bracket. So 2i plus 3j plus 4k is what I want. So I have defined it like that. So v is equal to vector in square bracket. I have to put 2, 3, 4. If I ask SageMath to print v, I'll be getting the output like this. See that I have enclosed it in a square bracket and then a what you call ordinary parenthesis, but the output is coming as ordinary parenthesis. But there is actually a difference if you simply put 2, 3, 4 in ordinary parenthesis and do not use the vector command. For example, suppose that I am writing u is equal to just this, and suppose that if I'm going to ask Sage to print this u, then also I will be getting exactly the same output. But even though these two objects v and u looks like the same, they are not exactly the same. To know that why they are different, let us see that what the type of this object v is. If you use the command type in Sage, you will see that v is nothing but it is an element of vectors with integer coefficients in some module. Sage module means that it is actually a library. So it is a member of integer vector. But on the other hand, if you try to see what type of object this U is, you will say that this is just a tuple. Okay, but what is the basic difference? These two are just names. Tuple, vector, all these are names. Suppose that we want to take a scalar multiplied with this V. So 2 star V. So 2 star V is nothing but 2 times the vector V. We get the result to be equal to 4, 6, 8. That is expected. 2, 3, 4 multiplied with 2 is 4, 6, 8. But on the other hand, suppose now that instead of that, if I see the difference you can see here. So what exactly happened here? Anybody can guess? 2 star U, I am getting it as 2, 3, 4, 2, 3, 4. But 2 star V, I am getting as 4, 6, 8. So what exactly happened here in the second command? So can anybody guess? Any guess from anybody?
It's just repeated that vector.
Yeah, 2, 3, 4 is again that U is appended to U again. That's it. U is appended to U. That's the only thing happening here. So instead of taking the product of 2 and U, what it did is that it took U 2 times. So that is because U is not expected to be an object which is supposed to be multiplied with a scalar, because we know that multiplication with scalar is possible only if it belongs to some certain set. For example, vectors you can multiply with scalar. If you have real number, you can multiply it with a real number. Real number you can multiply with integer. But U is something known as a tuple, and that is not expected to be multiplied with anything else. That is why you are not getting 2 times U to be what you expect, but 2 times V you are getting actually what you expect. Therefore, whenever you have to define a vector, you need to definitely use this vector command. Now, if we modify, if we change this U to vector U, suppose that we write U is equal to vector U. Let us see the effect of that. And after that, print 2 star U. So the output is 468. So what is that is what is expected. So here we are converting that U tuple to a vector by using the vector command. Therefore, to define a vector, either you have to define vector like V equal to using the vector command is compulsory. Either you can define in ordinary bracket 2, 3, 4, or you can use in square bracket U is equal to vector. In ordinary parentheses also you can put the same thing 2, 3, 4. And if you ask Sage if these U and V are same or not, Sage will say that it's true. That means that you can define, sorry, I defined both using the same bracket. No. At one place I wanted square bracket, at the other place I wanted the ordinary bracket. So in whatever way you define, the only thing is that you have to enclose it inside one vector command. So vector command has to be applied for converting a list or tuple. List means that whatever you are enclosing within square brackets. Tuple means that whatever you are enclosing, comma separated within ordinary bracket. So we can convert a vector, a tuple or a list into vector by using the vector command. So now what are the other options that can be supported by the vector command? We can of course add two vectors, print U plus V. Of course, U and V are taken to be the same here, but even then, U plus 2U plus 3V, that also can be defined. And of course, you cannot, if you try to take the exponent of this V, what will happen? Square. It will say that this is not implemented. That is, squaring a vector is not implemented. Then you have to either use V dot U or V cross U. You cannot take any V square. There is no point in using the command V square because vector is not supposed to be squared. Vector is supposed to be either taken dot product or cross product. Now, if you want to take dot or cross product, if you want to take dot or cross product, okay, let me define V to be equal to vector 1, 2, 3 and U to be equal to vector 3, 4, 5. Suppose I define two vectors. Suppose that I take print U dot I'm taking u dot product dot product. I'm not getting the command. Why it's not? Oh, okay, so dot product v, and if I ask Sage to print u dot product v, which is means that u dot v. Okay, why is it happening like this?
So spelling of product.
Product is wrong. PROD. Okay, PRODU. Okay, thank you. That's correct. So the spelling is of course really important. Dot product u dot product v. So what can be the equivalent command for cross product then? You can guess now. So this is the dot product. So command for cross product is u cross product v. That's it. So if you want to find dot product or cross product, you have to simply use u dot product v u dot cross product v. These are the commands that we have to use for getting dot product and cross product. Now we know that a normalized vector usually means that a vector divided by its norm. That can be easily found using the normalized command. Print u dot normalized. It is sometimes confusing that sometimes we are using the command before that object. So sometimes we write normalized of u, sometimes we use u dot normalized. This is basically happening because Sage is not a software written by one person. Sage is written by collectively by many software enthusiasts, many mathematicians from around the world. So some of them may be having the habit of putting this thing here in like this u dot. Some of them may be having the habit of using normalized of u. So sometimes it can happen that both these commands will work. Sometimes it will happen that only one way it will work. So to understand in what way it will work, the only way is to actually try using trial and error. If you're not getting that command by putting that command before the object, you have to just use the command after the object. But whenever you are using the command after the object, it is a standard procedure that you have to put an open and close bracket. So we get 3 by 10 root 2, 2 by 5 root 2, 1 by 2 root 2 as the normalized vector. Okay, if you want to see this vector plotted, that also can be done. So suppose that we want to see that where exactly this u is lying and where this normalized vector is lying. There is an easy way to plot that. So you need to just plot u dot plot. That's it. Or plot u, whatever. Now you can see that the vector is plotted here, but of course there is no arrow or anything like that. There is no arrow mark. You can see that the vector is, what was the vector u? We have 1 2 3. Is it going to 1 2 3? It is going to which direction? What is the vector that we plotted? V is equal to, sorry, 3 4 5, not 1 2 3. U is equal to 3 4 5. So in the x direction it should go to 3. Is it going up to 3? So that we need to see where is 3, x is equal to 1.0. Yes, most probably yes, it is going to 3. You can see 3 here, and y direction it is supposed to go 3 4. Is it going to 4? Okay, and we see that it's going to 4. Y axis we need to check. Yes, in the direction this is going to 4, and this is the direction it's going up to 5. This is what the vector u plotted. Now if you want to see, okay, we can turn off this frame, and maybe we can turn off. Frames equal to force, axis equal to true if you turn off. If you turn on frames, oh, but that is not accepted. That command is not accepted here. Frames is equal to axis turned on, but frames, this is not frames then probably. Is this box? Still it is not going away. Okay, let us see what are the parameters available for the plot command. Plot question mark. So if you see the options, scale, x minimum, x maximum, y maximum, legend label, color option is there, automatic, legend color, fill color, appearance options, alpha, where are the line options? We need to turn off the frame if we want. Okay, axis on or off, that is okay. Fill alpha, style sheet. Okay, I'm not seeing that option anywhere. Okay, there is an option probably for that, for turning off that axis. Anyway, we are just leaving like that. So if you try to plot the normalized
Sir,
vectors, yes, yes.
sir, when I tried to do it, I didn't get that axe points in the graph.
While plotting, what do you mean by points on
Yes,
the
sir.
graph?
That x equal to y x values and y values.
No, I didn't understand what you exactly mean. What you are saying is you are trying to plot some point and you are not seeing the points, or what is it
No,
exactly?
sir. I will try along the class.
You are just exactly the same command you are using.
Sir, when I use that command u dot plot and
Uh-huh.
close the bracket,
Uh-huh.
then I get only the figure only. There is no points.
Try to rotate it. Try to just rotate this.
Yes, sir.
If you're
There is
rotating, then
no.
also you are not getting it.
No, sir.
You are getting an empty
Only figure,
screen.
3D figure.
You are getting an
Sorry, sir.
you are getting an empty square bracket, empty square.
Ah, yes, sir.
Okay, and what are you seeing here? SageMath 9.0 or something else?
Yes, sir. Sigma 9.0.
Okay, then I will suggest one thing. Okay, let us just see. Okay, can you try this command extra, comma, viewer equal to 3js,
Okay, wait.
comma, viewer equal to 3js in quotes.
No, sir. Nothing.
So is it possible for you to share the screen?
Sir, actually, I am doing in my computer.
No, that's what I'm asking. If you're doing on the computer, are you able to share the screen? If you are able to share the screen, I can probably have a look at that. What exactly is happening?
Okay, so wait. Let's.
Okay, I'm stopping the presentation.
Can you see it, sir?
No, there is a share screen option. Present now. You can just okay.
Sir,
You are using mobile.
I think, yeah,
Sir,
yeah,
at the
she's
time only one.
You are using mobile and okay, but okay. This I cannot see. It's very difficult to see. Okay, let me see. I can pin. Okay, viewer equal to 3js. You are trying. So, but I am seeing a line there. I am seeing a blue line there.
Ah, yes, sir. Blue line is there, but
Then what else you want?
I want that points.
Oh,
X axis and y axis and z axis.
that measurements are not appearing.
Measurements of that.
Okay, but for me it's appearing. I don't know why exactly it's happening. Axis equal to true. Can you turn on? Axis equal
Okay,
to
wait.
true. Try that once. And remove box equal to false.
Mhm. Hello, so when I do that axis equal to true, I get some different color of lines in that
But still,
box.
even then, that x and y points, x and y values are not appearing.
Not appearing.
Okay, that I have to see. I don't know exactly why it's happening like that. Exactly the same command I'm using here. You are using Windows or Linux? What is it exactly?
Windows.
Now, maybe some problem. There may be some problem with this Windows version. I don't know exactly. I'm using a Linux version. Maybe there is a slight difference between the versions that we are using. Okay, we will see that. Anyway, this is the only command. There are no other extra options that I'm using. So I don't see any reason for that not appearing. Maybe that we are using different versions of Sage, and Windows maybe having some problem in that plotting. Okay, we'll see that. Anyway, we'll check that.
Okay, sir.
For the time being, we'll proceed and we will check that afterwards, because that's a problem specific to, I think, Windows. We need to check. Okay. So
Okay, sir.
this is one way to. Yeah, there is another way actually to draw this, which is that suppose we can draw it as the, here we are not seeing any arrow mark or anything like that. So if we want to see an arrow mark, like in the case of a standard vector, we may use the arrow command. So arrow, but in that case, we need to specify the origin, because arrow is usually from one point to another point. It is not like a vector; it's from one point to another point. So we need to define a point like origin. So I'm defining a point uh, 0, 0, 0, and then I'm going to plot an arrow from origin to the vector unit. Let me see if it's working. So can you just try this arrow command and see if it's working for you? P equal to arrow from origin to u. Now p dot show. Maybe the show command will be maybe sometimes helpful. And try to rotate. So in this way, we will get a vector looking like object, because previously we had only one line, but here we are getting a vector looking like object. Now, in the same way, we can draw the normalized one also, from origin to u dot normalized. If you do that, you will get two vectors, but unfortunately, to see both these vectors, you need to probably what do you need to show? Okay, p plus we should do, and we need to also give some different color for that. Otherwise, they will look the same. A color equal to say green, extra quotes, color equal to green. So if you do that, okay, we can say that one vector is appearing here, one vector is appearing here up to here. This is the normalized vector, and the other vector is going up to z equal to 5. So there are two vectors, but both these vectors are in the same direction. The normalized vector will be in either in the same direction or opposite direction. Here it is in the same direction because both are going upwards. So this is how we normalize a vector and draw the vector and normalized vector. The command I used is for plotting, it is arrow. So this is how we plot vectors in the plane. How we handle the vectors in the plane and plot the vectors in the plane. So in this way, we can plot any kind of vectors we can plot, and of course, we can perform some projection, the projection of vector on some other vector. That also can be done, but for that you need to do some extra mathematics. It is not that straight, but some extra mathematics is required for that. Now, one more thing I will just try to explain. That is about plotting parametric equations and vector equations in this space. So the command I'm going to use is, suppose that I define r of t is equal to cos t vector cos t sin t and t. Now, if second semester students are not second semester, if what semester is that? Third semester. Now it's third semester or fifth semester. So second and third and fifth semester students will be able to understand that this vector equation actually represents a curve called. Can somebody answer? What kind of curve is going to be represented here? Okay, we will see that P equal to parametric plot. Because there are three, we will see a three-dimensional vector, three-dimensional plot R of t in the range. What range we should put? We can put the range to be t in the range, say 0 to say 5 pi, something like that, and with some color. What color? Black. See the output. Parametric plot 3D R of t within this range. Parametric plot cos t. Okay, cos t is not defined. What is next? Sin t. Okay, symbolic expression is not able to convert. So instead of that, vector command, we will just use it as the tuple, three tuple, and we'll use this just like this. And see, okay, the vector command is now removed. This is just a parameter. See, vector command can be used only if you are using concrete numbers. You cannot use functions there. That's the problem here. So if you plot, I'm getting something like this. Can somebody identify this curve? What is this?
Circular helix.
This is a circular helix, exactly. Now, if you want to plot an arrow also, so that also can be done. P plus equal to, suppose I'm plotting an arrow from, so the R is already there. So how do I do that plotting an arrow from, so origin is also defined. So arrow is therefore from origin. I'm going to plot a vector from origin to that vector parametric curve. So origin to R of t, substituting t equal to where I should plot, say pi. P plus equal to, so there is no space here, P plus equal to origin from R dot subs. That is from R dot substitute. You can see here. See, what is this now? So from the origin, which is the center, so we should probably turn on axis also. Axis equal to true, frames equal to false, but frames is not going away. Is it like that? Previously we turned off frame. So how was that? Frames equal to false or frame equal to false? Okay, it's frame equal to false. Correct. So, but axis also gone there. Axis equal to true. Okay, T is capital. Axis equal to true. Oh, but it's very small axis. Axis is very small here. But anyway, axis has come. Maybe we need to specify the range of this plot also, but range is already specified here as t from 0 to pi. Maybe the x and y axis also we have to probably specify here, but we are doing everything in parametric terms. So if I specify x from -5 to 5, let me see what happens after that. Positional argument. So this is not correct. So somehow we have to increase the axis size. I need to check that command. So anyway, this is the way we are plotting a parametric curve and a vector to that. So a parametric curve is plotted and a vector also to that is plotted. Now let me just reduce this value to 2 pi so that we can see it fitting into this. So this is the axis we have. This is the vector we have. So helix is drawn now, and a vector is also drawn to that helix. Now, to find the tangent vector, okay, frame also I will turn on. That is better to see. This is a frame here. Now, to find the derivative, say r1 of t equal to, we can differentiate and find differentiate with respect to t. So we get the derivative of r of t to be equal to, so what is the derivative? Where is that appearing? Diff r of t, print r1 of t. What is the problem here? Derivative, we need to see, this is the symbolic minus sine t cos t 1. So that expression is got now. So what is the problem here? Diff equal to, maybe we should try to convert this into a vector, because differentiation, some of the functions will apply only on vectors and some of the functions will apply on non-vectors. So, oh, even here it's not working. What is the problem here? Unable to convert minus sine t cos t 1 to a symbolic expression. So maybe instead of doing all these things, I will just ask to print this. Let us see if he is able to print this. Suppressing this. Now it's coming, because it's not. It is not asked. It is not permitting us to assign this to some r1 of t. That is the problem. But why is it like that? Okay, we will just put r equal to instead of that. R is equal to no more variables. So r is equal to this. And now let me print not r, r1, r dash. Print r1. We ask him to print r1. Am I getting some result? Okay, here I'm getting the result. So derivative I'm getting. Now to plot the tangent vector corresponding to this t naught equal to pi, or okay, t naught equal to pi. So corresponding to t equal to t naught, we can plot the tangent vector in the following way. So no show now, show will be done later. So we'll plot one more vector here, arrow from origin to r1 dot substitute t equal to t naught, and let us see the output. So do we have two vectors now? Where are the two vectors? We have only one vector. Where is the other vector? Okay, what is the command that we have given? Origin to r1 substitute t equal to t naught, p dot show. Okay, what is the vector that we are getting here? Are we getting the same vector here? No, cos t sin t 1. So one means that should go to one height. So let me just try to see if I change this to pi by 2, what will be the output? But that vector is not appearing anywhere here. Why is it like that? So one vector is here. Have I drawn two vectors? Oh, instead of that, I just instead of copying and pasting, I cut that. Okay, sorry, that's a mistake. I did not copy paste, but instead of that, I was cutting and pasting. So I need to do r dot substitute also. So I'm using only one command instead of only one arrow I was using instead of two. Okay, now I have two arrows. So now how do we see, how do we know that which arrow corresponds to what? We'll give probably some color. So let us give some color, like color equal to green, and color equal to, so which color? Red. And see. So the red colored one is the tangent vector. Red colored one is the tangent vector, and the green colored one is the actual vector. So we have plotted the tangent vector and the actual vector. So this is how the tangent vector looks and the actual vector looks. R of t naught and r dash of t naught. Now, if you want to draw the actual tangent line itself, suppose that we want to draw the tangent line that passes through the endpoint of the green vector, which is a tangent line to this parametric curve. So we know that there is an equation for that. So what is the equation for that? The equation for the parametric curve is it's nothing but r equal to, equation for the tangent line is equal to nothing but r is equal to r of t naught R dot substitute t equal to t naught plus the equation is this plus what is that t star r1 t naught. So this is the equation of the vector equation of the line which is tangent to the curve at t is equal to t naught. R substitute t equal to t naught t star. Okay, but it is not asking. It may ask now that what this t is. So you should declare t to be a variable. So if we give this r is equal to, okay, let us see what the output is. Print r. What is r printed? VAR L. Sorry, that's not correct. VAR. Now what is the output? Not able to determine substitution from 1 by 2 pi. Substitute t equal to. Okay. So we are getting the equation of the tangent line, the parametric equation of the tangent line as what is the parametric equation? Minus t 1 by 2 pi plus t. This is the parametric equation of the tangent line. Now, if you want to plot the tangent line, we can plot it directly using the parametric plot. We plot it using the parametric plot. So, p plus equal to parametric plot. Oh, but there is a problem. We are keeping on changing this r. Okay, that is not probably going to make any problem for us. But instead of r, probably we will make r2 or s. I think that's better. S is equal to so parametric plot of s in what range? Okay, in some range we are putting. So let us see the output of this. Are we getting a tangent line finally? What is the color that we have given? Color equal to. So what is the other color that we can give? Maroon or yellow? And maybe from instead of 0 to 2 pi, we will put some minus pi so that we can see some left side also of the line. Okay. This is the tangent line, and you can see that the tangent vector, which is the red vector, that is parallel to the tangent line that we are plotting at the point r t naught. And if you want to mark the point, that also can be marked. The point t naught also can be marked. So p plus equal to point. Which point we should plot? R substitute t equal to t naught, and maybe the size of the point should give something large, and color equal to some color black. Okay, show point r substitute t equal to t naught, size is this. What is the mistake here? Pre-module object has no attribute substitute. Okay, size equal to 30. Okay, we are seeing something here. I think you can see that there is a point appearing here. Maybe we should increase the size further, because compared to the size of the graph, it is very small. So okay, 30 itself I will give, not 300, 30 itself, and I will reduce this 2 pi to say just pi. You can see that a point is appearing there. Maybe we'll increase the size further, 50. Okay, now you can see that the tangent at this point, you can see the vector is pointing to that particular point. The vector RT node is pointing to that point, and tangent vector is parallel to the tangent line. Everything is visible here. So this is how we plot a vector violet, the parametric curve corresponding to a vector violet function, a tangent vector, and a tangent line passing through the endpoint of the tangent vector. This is how we do all these things. If you have any question, you may ask me now. If somebody is typing, then they can finish the typing now, and I will proceed after that. I think this is quite useful for teachers, especially when they are trying to show the students how to plot this parametric curve, how to plot tangent lines, etc. So if there is no question, I will proceed further. Okay, then I am now moving towards linear algebra, and the notation of the linear in linear algebra also we will be denoting the rows, etc., just like vectors. There is not much difference between row vector and vector, but of course we'll be using some commands specific to linear algebra and some command like matrix. So now we are moving to linear algebra. Okay, the basic thing that we usually require in linear algebra is to know how to define a vector. So defining a matrix. Defining a matrix in Sage is very easy. So you need to just use the command matrix, and then you can define the vectors in two ways. One way is to specify all the rows. You need to specify all the rows as comma separated list, and then press the enter key like this. Matrix. So one square bracket opened. Now, actually, I need one more square bracket. So here I will be enclosing all the rows. 1, 2, 3. This is one row. 4, 5, 6. This is another row. 7, 8, 9. This is another row. Matrix. And if we ask Sage to print it, print A, we will get it in the matrix form 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you want to see it in a little bit better form, you may use the show command. Show command we have already used for showing plots, but show command can be used even for showing objects in Sage Mathematics, which is more friendly to mathematics viewing like this. So if you use show command, you will get 1, 2, 3, 4, 5, 6, 7, 8, 9 in the matrix form itself. And on the other hand, if you use the LaTeX command, you will get actually the LaTeX code corresponding to this matrix. So LaTeX A. See, this is the LaTeX code for preparing a matrix like this. So you can copy and paste this LaTeX code anywhere in your LaTeX document and use it. So this is how we create a matrix. There is an alternate way also. If you do not want to put too many brackets, then another way is to define something like this. B equal to, specify the dimensions. If it's a 3 by 3 matrix, just say 3 by 3. If it's a 3 by 4 matrix, say 3 by 4, and enclose everything inside one list. No need to put extra this. But this can be sometimes confusing, but this is easy for typing. And in this case, you don't need to put extra brackets here. One bracket is enough. Print B. And if you ask whether the two matrices you defined are the same, A equal to B, answer is yes. So you can define matrices in two ways. One way is to just enclose the rows in square brackets and put everything inside another square bracket, another pair of square brackets. And the other way is to just specify the dimension of the vector, just like m by n matrix, m, n, and then enclose everything inside one single list. These are the two ways of defining a matrix. Now, If you want to define some standard matrices like identity matrix, etc., there is an easy way to do that. Instead of typing 1 0 0 0 1 0 0 0 1, etc., we can straight away define identity matrix in the following way. Suppose that we call I3 as print equal to matrix dot identity 3 and ask SageMath to print it. So we will get 1 0 0 0 1 0 and 0 0 1 as the identity matrix. So this is the easy way to create the identity matrix. And of course, you can multiply matrices with scalars like print 2 star I3. You get the result to be 2 0 0. You can add also print A plus 2 star I3. So we will get it to be this. And now inverse of A can be found provided it has determinant non-zero. A dot inverse. So we get A dot inverse. If you try, we are getting because zero division error, because matrix must be non-singular. Therefore, before trying to invert a matrix, we need to check if it's invertible or not. So if, okay, before that, let us see the determinant of A, dit of A. You get it to be equal to 0. So our determinant is just dit. There is no long command for that, just dit. So we will decide if determinant is non-zero if dit of A not equal to 0. Print inverse of A exists and is A dot inverse, or else print A not invertible. So in this case, A is not invertible. Now, on the other hand, suppose that we give, instead of A, suppose we give I3 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 I3, we get the inverse of I3 exists and is 1 0 0. On the other hand, we can of course try the inverse of 2 times I3 also, and we will get the inverse of 2 times I3 to be equal to, oh, what is happening? 2 times I3 inverse. Okay, this 2 0 0 is coming on this side. So 2 times I3 inverse. And is, maybe we can put a new line so that it will appear on the next line. So inverse of I3 exists and is 1 by 2 0 0 0 1 by 2 0 0 0 1 by 2. This is how we find the inverse of a non-singular matrix. So just use the determinant command to check if it's invertible or not. If it's invertible, we can find the inverse using the inverse command. But of course, we can find the inverse using the raised to the power -1 command also. That is also possible. For example, suppose that b equal to 3 star I3 and print b to the power -1. We will see that 1 by 3 0 0 0 1 by 3 0 0 0 1 by 3. So therefore, instead of using the inverse command, we can straight away use b to the power -1. So b to the power -2 also will work. Same. So b to the power 2 also will work. So all these things will work. So once you create a matrix object using the matrix command, any of the operations that we usually perform over matrices can be performed here. So this is quite easy. Now, what is the next thing that we usually want about matrices is that to find the characteristic polynomial, to find the eigenvalue, etc. And of course, there are several other things also, but before that, we'll go to the characteristic polynomial related stuff. So if you want to see the characteristic polynomial, we usually compute using the command that a minus using the matrix a minus xi. So we need to define a variable x first. Variable x. So variable x is defined. Now a is already defined. Let us redefine it. A is equal to, what is the command that we used? A is this matrix. Let us see if x star a works. Print x star a. Okay, that works. But we need x star i3, not x star a, i3. What is x star i3? X star I is just this. Now to find the characteristic polynomial, we need to take the determinant of a minus x star I. Okay, ch only equal to determinant of a minus x star i3, and print it. We get it to be equal to this. And if you want to see this once again in some neat format, better format, use the show command. So you get this to be equal to minus x minus 5. It's already splitted. This is not expanded. You are getting it to be equal to minus x minus 5, x minus 9, minus 48 into x minus 1, 29. So this is a cubic polynomial anyway. So this is a cubic polynomial. This is how we find the characteristic polynomial. And if you want to expand this polynomial, that is also possible. And for that, you may need to, but in the case of for finding characteristic polynomial, we actually need to solve it instead of expanding it. For expanding it, sorry, for solving it, we can use the solve command that we have seen previously. Print or solve characteristic polynomial. We use solve characteristic polynomial for x. We get the output to be x is equal to minus 3 by 2 square root of, okay, maybe I can show. We get the answer to be x is equal to minus 3 by 2 root 33 plus 15 by 2, x equal to 3 by 2 root 33 plus 15 by 2, x equal to 0. These are the three characteristic roots or eigenvalues. So this is how we find characteristic polynomial in SageMath. So what are the steps that we followed? We initially constructed x star i3, then we took determinant of a minus x i3. After that, we asked SageMath to solve characteristic polynomial, and the solution turns out to be equal to the characteristic values or eigenvalues. But instead of finding the characteristic polynomial like this, there is actually an easy way in SageMath. That is just to use the characteristic polynomial command. A equal to a dot characteristic polynomial will actually give, see, this is actually a better way of looking at this. See, here this is not actually expanded because we are trying to solve something, but the characteristic polynomial method available in SageMath will automatically give the answer to be x cubed minus 15x squared minus 18x. Now, either you can solve it, or instead of even solving this polynomial, we can directly also find the eigenvalues. A dot eigenvalues. But here we are getting it to be something approximate because eigenvalues that function returns the result as numerical approximations. Therefore, if you try to use that, it is always better to use a dot characteristic poly for finding the characteristic roots, and then use the then try to solve it for finding out the characteristic roots. So that is actually much better because here we will be getting something approximate. But if you're trying to solve a dot poly, you will be getting something exact. This is how we solve for finding characteristic roots and characteristic values of a matrix. Now, to find the transpose of a matrix, now we can guess that the command is going to be a dot transpose. Okay, we'll print A and A transpose simultaneously. Print A transpose both. Maybe one new line is also required. New line character is \n. Transpose once again. So we are getting the transpose to be equal to 147,258,369, and you can see here that 147 is the first column, 258 is the second column, 369 is the third column, and that could change to first row, second row, and third row. This is how we find the transpose of a matrix. Now we can form the augmented matrix also in the same way. To find the augmented matrix, we need to what do you call it? Take a row vector, and then we have to augment that row vector. Sorry, not row vector. So column vector. You have to augment that column vector to the matrix. So you will see we see that also here. Suppose that we define B to be equal to matrix. But here, not that we did define it as a column matrix. So, but instead of that, what I will do is, okay, I will define it to be 1 or 10, 10, 10. So this I want to be a column matrix, means that there are 3 rows and 1 column. So I can just split it like this. So 10, 10, 10. And if I print B, what will happen? 10, 10, 10. Now to augment C equal to A dot augment B, and if I print C, I'll get 1, 2, 3, 10, 4, 5, 6, 10, 7, 8, 9, 10. This is how we prepare the augmented matrix. Now, if we have a system of equations to solve, we know that the system is going to be consistent provided that the rank of the original matrix is equal to the rank of the augmented matrix. But in this case, we need to find rank of matrices. For finding rank of the matrix in Sage, we use the rank command. A dot rank equal to 2 C dot rank, which is the augmented matrix, equal to. So since A dot rank is equal to C dot rank, we can say that A and C are the system of the linear equations corresponding to Ax equal to B is consistent. So this is how we check the consistency of a system of linear equations. So if A and augmented matrix are having the same rank, then they are consistent. So this is the beginning of how we solve system of linear equations in Sage. We can find the augmented matrix. We can find the rank of the augmented matrix. We can find the rank of the original matrix, and if we compare them, if we get them to be equal, the system is consistent, and therefore there are solutions. Now the question is about how to find solutions. If there is some question regarding these things, you may ask now. So I think there are no questions, though. So I will continue with this. And this is how we find, I don't know that the linear algebra is not actually being learned by the students now, right? Linear algebra will be learned only in the next semester, I guess. There is no linear algebra, I think, in the first, second, third, and fourth semesters. Is that correct?
Yes, sir.
So are they learning this? Yeah, are they learning this linear equations and solutions of system of linear equations in their +2 classes?
They are finding the solution by using that inverse method. Only by finding the inverse method. X is equal to A inverse B.
Okay, so they need to just find X is equal to A inverse B. That's it. So,
Yes, that's the
but that we have already done. That we have already done because we have already seen that how to find the inverse of a matrix, and we now know that how to find the product of two matrices because we can take A inverse into B. So, solving them using the inverse that we have already seen. And what are the other things that is there in the linear algebra syllabus? So they're not learning anything, right? So they're not learning anything extra in linear algebra. So what else can be useful for them then in linear algebra? Is there anything else that you have some suggestion? Because if we say something in linear algebra that is not applicable or not understood by the final year students, they will not understand anything.
yes, sir. That's
Because I think these are the
that will
only,
be
yeah.
that will be a problem for them. So
So how to do that is okay. Mm, what are the other things that they require? So solving
I think we can do one problem using this method.
which problem? Which you
By,
using
by using
using which method?
by using by using the rank, if the students is understanding, then they can go to the more problems. No?
Okay, that is also possible. The only thing is that we need to. Okay, so I will try to explain that. I don't know because the only problem is that if they have not gone through this linear algebra and reduction to echelon form, etc., kind of thing. Uh, so using Sage, they may not find it to be interesting. That is the only worry I have. So if we just
Okay.
say these things, of course we can do that, but still, okay. Let us see one system of equations and try to solve that. Okay, suppose that system of equations we have is something like suppose we take A to be equal to what should we take? A to be the matrix 3 by 3 or I will take a simple matrix 3 by 2, so 3 variables. So how many variables will be there? 3 variables and 2 equations. Therefore solution will be there 3 2. So what should I take? 1 2. So total 6 elements are required. 3 6 8, something like that I should take. 3 6 8. Okay, let us see. Try randomly. We will try something. So A is this, and x is the coefficient. X is the variable matrix, and suppose we define x to be equal to. We will define A, B, C to be variables or symbols. A, B, C. While we have to find x is the variable matrix. Therefore, x is equal to matrix 3 3 rows, 1 column. So A, B, C. Now the right side is B equal to, say, some two numbers I'm choosing. 1 matrix. So what type of matrix I should choose? 3 by 2 by 1. 2, 1. And after that 2 by 1, 2, 4. Some two numbers I'm choosing. Okay, let us see if everything goes fine. Print A star x and okay, let us see A star x. Will it go fine? Okay, print A. What is there? Let us see. We print A 1, 2, 3, 4. Okay, we require 2, 3, not 3, 2, 2, 3. Therefore, that can be multiplied with the 3 by 1 matrix. Print A star x. Here we are getting something like this: A plus 2b plus 3c, 3a plus 6b plus 8c. A star x equal to A star x equal to B. A star x equal to B. So we are getting, okay, instead of this, we will print B on the next line. So the system of linear equations that we have to solve is this. A plus 2b plus 3c is equal to 2. 3a plus 6b plus 8c is equal to 4. This is the system we have. Or we can even reduce it to two variable, that's also possible. A plus 2b, 3 plus 6b. A plus 2b, 3 plus 6b. Okay, this is, I think, okay. We'll just see what's happening after that. So a system of equations we have to solve is A plus 2b plus 3c is equal to 2 and 3a plus 6b plus 8c is equal to 4. This is the system we have. So we will check the rank first if this is solvable. Rank of A is 2. Print rank of A dot augment B augment. Okay. AUGMENT A dot augment B, that is also 2. Therefore, solution is definitely there. Now we are going to row reduce this. So for row reducing, what we usually do is we will convert this into something known as echelon form, and the echelon form of the augmented matrix is no need to find the echelon form of the okay. We have to find the augmented matrix. We have to row reduce the augmented matrix, and after that we will see. So the augmented matrix we will call as AM. AM equal to A dot augmented with B. So what is AM now? AM is equal to this. So now I'm going to row reduce this using the command echelon form A dot or AM dot echelon form. I'm getting to be equal to this 120 minus 4 0 0 minus 2. So how do we interpret this? So the interpretation of this is A plus 2b plus 0c is equal to minus 4. So we have to interpret in this following way. So we have to interpret it like A plus 2b plus 0c equal to minus 4 and 0a plus 0b plus 1c equal to 2. So from this we will get this is 0. Sorry, this is 0. This is also 0. From this what we get is c is equal to 2. So we get c is equal to 2 and a plus 2b is equal to minus 4. So a plus 2b is equal to minus 4 means that you can give whatever value you prefer to b and a has to be decided according to that. C we have already got to be equal to 2. So this is how we solve a system of linear equations using echelon form or row reduction form. So this is how we are reducing a matrix to its reduced form. The command we have to use is echelon form. But if you are trying to solve it using the inverse command, the problem here is that you cannot actually find the inverse because here the matrix is 1, 2, 3, 3, 6, 8. So if you try to use the matrix the inverse of this, you cannot invert it because you know that square matrices only can be inverted, and that also provided that it is not singular. Here A is not a square matrix, therefore you cannot invert it. Therefore you have to find some other way, and the other way is known as reducing the augmented matrix to echelon form. So we get the augmented matrix reduced to echelon form to be 1, 2, 0, minus 4, 0, 0, 1, 2. You have to interpret this as 1 into A plus 2 into B plus 0 into C equal to the right side minus 4. Similarly, 0 into A plus 0 into B plus 1 into C equal to the right side 2. This is how you have to interpret this set system of equations reduced into some other form. So if you interpret it like that, you will get C to be equal to 2. But here is no C here because coefficient of C is 0 here. Therefore, you will get that A plus 2 be equal to minus 4, or if you put some value for B, suppose that you are putting the value of B to be equal to 1, then you will get A plus 2 equal to minus 4, or A is equal to minus 6. So you can find solution for the system of linear equations using row reduction, or something known as using the echelon form of the matrix. So this can be applied to any type of matrix. Singular matrix, it can be applied, a non-singular matrix, and the square matrices, non-square matrices, anything. So this technique is applicable to anything. Now, what is left after this? Okay, let me go to some vector calculus itself. I think those are the things that they are learning, and they may be comfortable with that probably. If I go to vector calculus, parametric plot, that we have already done. The curvature. So the fifth some students they are familiar probably with the finding curvature, right? In the case of vectors,
Yes, sir, we know.
vector valued function and finding. You know that for finding the curvature, we have to what we usually do. We need to differentiate. Suppose that r of t is the function given, so we need to differentiate r of t. Then curvature is defined to be, and even before finding the curvature, you know that we can find something known as a normal vector, tangent vector, etc. Right? So the normal vector, we have already seen how to normalize a vector. Now to find the what you call tangent vector. So how do we plot the tangent vector? Tangent vector also we have seen already. And after that, curvature, we know that. So the definition of the curvature, we know that it's equal to norm of derivative of r cross product second derivative divided by norm of the derivative taken 3 times. Okay, so we will see how to find the curvature. Now we will insert a cell here. Finding curvature of a vector value function at t naught. Suppose we define r equal to some function cos of t, sine of t. Maybe we can define this to be a vector. That's better. Cos of t, sine of t, and t. Now this is defined to find the curvature. Now we have already seen how to plot this. Now we will differentiate this. Suppose that we call dr to be the derivative. Dr equal to differentiate r with respect to t. Let us split it. R dr. So we get the derivative to be this. Now to find the curvature, we know that the formula is the following. Curvature is defined to be curvature equal to, how do we define curvature? It is equal to norm. For finding the norm, the command is this norm. Norm of derivative of r. What is the command? Cross product. Cross product with, oh, we need a second derivative also. So second derivative, let us just define it as d dr, double derivative, to be equal to differentiate. We can differentiate dr once again, or anyway we can differentiate either r 2 times, or we can differentiate dr once. So this is cross product with ddr. Now divided by we require this to be norm of this divided by, so now we have to close, divided by norm of r dash t cube, or r dash is nothing but dr cube. This is the equation for curvature. Okay, let us see the curvature. Curvature at sub t. This is the curvature at t. Okay, now ddr equal to, not minus, equal to. So we get the curvature to be this function. Curvature is equal to this. Root of modulus of cos t square plus sin t square the whole square plus cos t square plus sin t square divided by this. Now we will find the curvature at some point. Print the curvature of at what point t equal to some value, t equal to, substitute t equal to 0. So we'll get the curvature at t equal to 0. The curvature here is 1 by 2. Now we will print the curvature at t equal to pi by 2. So that is equal to 1 by 2. Let us see the curvature once again. T equal to pi by 3. Curvature is again 1 by 3. So can somebody answer that why the curvature is turning out to be the same for all these values? Can somebody say why it's like that? We will do some plotting also. Plot, parametric plot, dimension R within the range t0 to 2 star pi. So we have tried the curvature at points. What are the points? Pi by 2, pi by 3, 0. These are 3 points where we tried the curvature. So, okay, we will mark those points also. So this is P. P is this. We will add the point corresponding to R dot substitute t equal to 0, and maybe the size we will make it something large. Oh, we didn't ask to show p dot p show. If you show that, we will get where is that point? I'm not seeing that point anywhere. It corresponds to what value? Curvature point R substitute t equal to 0. Point at 0, maybe some color also I should give. Color equal to yellow or green. Oh, why is that point not appearing anywhere? Is it coming anywhere? Did I add? Okay, let me see. P plus is equal to point. That's correct. P plus is equal to point. Substitute R dot substitute. T is equal to 0. Okay, let us try to plot one more point and see if it's appearing at pi by 2. T equal to, what is the mistake here? T equal to, oh, there is a mistake. Space here. Okay. Plus equal to, there should not be any space. Even now it's not appearing. P plus equal to plot this, print curvature. Oh, but finally we are again plotting this. This is wrong. So only this plot is appearing. Okay. Okay, now it's appearing. So these are the 2 points where we are not the 2 points, 3 points actually. We have found the not 20, some smaller value. So 20, 20, and the output is it's here. So here there is 1 point, here is 1 point, and one more point we will probably give P plus equal to substitute. This is equal to what is the third value that we have given? It is pi by 3. So one more point, one more dot. So now the question is, at all this point, each and every point, t equal to pi by 2, t equal to 0, t equal to pi by 3, everywhere we are getting the curvature to be equal to 1, right? But why is it like that? Is the curvature a constant for this curve? What do you think? Is the curvature a constant for this curve? Can somebody answer from looking at this formula that we have already derived a formula? Cos t square plus sin t square the whole square, modulus of cos t square, modulus of sin t square, and even below that, modulus of cos t square plus modulus of sin t square plus 1 the whole raised to 3 by 2. Can somebody say that why we are getting the curvature to be the same always? Or are we going to get the curvature same always for every t? What do you think? Anybody can answer? Any answer to this? See, the only thing that you have to observe here is that here, of course, of the formula, you can guess that this is going to be equal to 1 by 2 always, because here you are getting cos t square plus sin t square, and cos t square. Yes. Somebody saying something? Okay, nothing. So from this formula, we can see that cos t square plus sin t square is always going to be equal to 1. Now, modulus of cos t square plus modulus of sin t square is also going to be equal to. The only thing is that we are taking them to be positive. So if we are taking them to be positive, then also it's going to be equal to 1. So what do you think? Is it going to this is going to be 1 or something else? So maybe this is going to be 1 plus 1. Okay, and below that, what is this? 1 plus 1, that is 2, and below that it's going to be equal to 1 plus 1, that is 2, 2 raised to 3 by 2, and root 2 is there on the top. So this is always going to be equal to 1 by 2. That is obvious. From the formula, this is obvious that it's going to be equal to 1 by 2. But now my question is not that. Can we say geometrically, can we explain the geometric reason for the curvature to be the same throughout? So for that, we need to understand that what exactly the curvature means. The curvature means it is a measure of turning of the curve. The curve, this is a circular helix. So sin t, cos t, sin t, t. So circular helix, the turning is the same everywhere. For any value of t, the turning is constant. It's constantly, it's turning at the same rate. There is no sharp turning or anything like that. So if you want a sharp turning, you need to probably give some extra multiplication to, you need to perform some extra multiplication to cos t sin t, because even if you multiply with the variable t, the change is not going to be that much visible. There will not be any change. But if you change sin t or cos t, and if you multiply sin t or cos t, you will be getting the curvature to be different at different places. You can see that here. Suppose that we multiply this with 2. So the curvatures are going to be 1 by 5, 1, this. You can see it here. See, the curvatures are different because the turning is different. The turning is not exactly the same at each and every place. where that curvature is more. From the origin, when we are starting, what is the curvature? It is 1 by 5. So when we are moving upward, the curvature is it's becoming more. When we are moving further downward, okay, maybe we can try the numerical approximation also. N of this, if you try, you'll get 0.59. Then the curvature is again coming down. So the curvature is fluctuating here. So if you change the variable, if you change the parameter from second parameter from sin t to 2 sin t, so there is a difference. So the sine part is contributing much. When sine is increasing rapidly, the curvature also will be increasing more. So in this case, the curvature is varying. But in the previous case, see, in the case of circular helix, basically we have a circle lifted upward. So in the case of a circle, we have constant curvature because on every point on the circle, the turning of vectors throughout this circle is a constant. There is no sharp turning or anything like that. Always it's turned in the same pace. So that is why we are getting the curvature to be constant throughout the circular helix. But if we change instead of sin t to 2 star sin t, the curvature also will be sometimes it will be more, and sometimes at some places it will be small. This curvature is actually a measurement of the degree of turning of the curve. That is why we are getting the curvature to be the same for circular helix everywhere and slightly different if you are using not circular helix but some other curve. This is how we find the curvature. This is how we plot the points. And of course, we can plot the tangents also. I have already told how to plot tangents at these points and how to plot vectors to these points. All these things we have already seen. Now, going further, suppose that we want to find the normal vector, we know how to find that. Normal vector is nothing but it's equal to, tangent vector is nothing but it's equal to derivative of vector divided by a unit tangent vector, not tangent vector. Unit tangent vector is derivative of the vector valued function divided by its norm. So we can define tangent vector like this: T unit tangent vector is equal to dr divided by, so dr will not work, norm of, no, dr will work, dr divided by norm of dr, and we get the unit tangent vector to be equal to this. It's a complicated expression, but if you substitute some value, you will be getting something better. And now the normal vector also can be found in the same way. How do we find the normal vector? For finding the normal vector, we have to differentiate the unit tangent vector, and then we need to take the what do we need to take for finding the normal vector? The norm of the second derivative of that we need to take. So the normal vector also we can find the same way. So I'm not going to explain that because I think once you know the formula, you can directly do all these things because you know how to find the norm, you know how to differentiate that, all these things, you know. Therefore, there is no point in explaining those things. You can find that. Now, what is the other thing? So, is there any other thing that we can discuss in vector and linear algebra that to which the students are familiar? If there is nothing else, then we can probably go to some calculus or something like that, or some other topic.
Divergence and curl is there, no?
Divergence and now we are going to see how to define the divergence of a vector field. Define three variables first: x, y, z. Now the components f1, f2, f3. Say f1 is equal to sine of x, f2 equal to cos y, and say f3 equal to sine x star cos y, something like this. And now we define f is equal to vector with these component functions f1, f2, and f3. Let us see what the function is in print f. We get the print to be equal to something. Okay, var x y z we should have given like this. Okay, now the print is this sin x, cos y, sin x. This is the vector valued function that we have. So if you want, we can actually plot and see what exactly the vector field, how exactly the vector field looks like. So we use plot and vector field, plot vector field 3D. We use the function, and the function is f, and the range is for x we will give say -2 pi to 2 pi, and for y also we can give the same range. Z also we can give the same range. So x and y we are giving the same range, and let's see the output. This is y, this range is for y, and this range is for z, and see the plot of this. And the plot comes something like this. See, you can see that the vectors are distributed like this here. So all these vectors are here. This is the vector field corresponding to this function f. Now let us see how to how to define the divergence. So defining the divergence, we know that we need to differentiate f1, f2, and f3 with respect to x, y, and z separately. So div f is equal to differentiate f1 with respect to x, and then plus differentiate f2 with respect to y, and plus differentiate f3 with respect to z. And let us see the output now. We differentiated all these component functions, and the print gives div f to be equal to cos x minus sin y. Now if you want to substitute this, if you want to find the divergence at one particular point, we may substitute that with the values, and we get print. This is okay. We will slightly modify it. Divergence of f, divergence of f is okay, somewhat neatly formatted. Divergence of this is cos x minus sin y. Now we okay, the plot is not visible, so we may just type p is equal to this, and give the plot also here, and show the plot just above this, p dot show. So now the output is this, and then next the we can see that the divergence we can substitute by using the command, okay, by using the substitution command, divergence at point say so 1, 2, 3. Suppose that this is the point that we are giving. For that we need to substitute div f subs x equal to 1, y equal to 2, z equal to 3, and let us print it, and we get the output to be equal to sin x cos y. This is the output. Divergence of divergence at 1, 2, 3 is cos 1 minus sin 2. So this is how we calculate the divergence of a vector field. Now we are going to compute the curl. The curl, for finding curl, there is a built-in command available. So if you want to find the curl of this, maybe I can use the next input cell. CF, suppose I call that to be equal to CF. So that can be found directly using the curl command. Curl, and I need to specifically mention the variables here, x, y, z. So this is the curl. For finding curl, I don't have to do anything extra. I can just straight away find, I can straight away use the command curl. That's it. Now, if I want to plot this, okay, let me plot this p, let me plot this function vector field, and together with that, let me plot CF also. CF. So what do I get? Let me show that. P dot show these are the things I'm getting extra. Am I getting something extra, or am I getting exactly the same thing? You see, once again, there is no curl here. So am I getting some extra vectors here? You can see that. These are the vectors if I am just plotting this F vector field. If I am plotting the curl also, they are also vectors. I will be getting some extra vectors here. Or if I plot only the curl along, see, this is much more stabilized. This is much more stabilized than the original vector function. That's because you can see that this is nothing but this is equal to minus sin x sin y minus cos x cos y 0. But what about here? Here you are getting where is the original function? The original function is where is that? What happened? Okay. Sin x cos phi, sin x cos phi. These two functions are sin x cos phi. The last parameter is causing some problem here, but here the last parameter is just 0. Therefore, the z parameter is 0. Therefore, we are getting everything. See, how do we plot this particular vector? Suppose that we have vector here it is equal to 1, and suppose that here it is equal to 1 2. So the same 1 2 vector you are placing at each and every x y z. So that the vector 1 2, I'm calling this vector to be equal to say 1 2. So this vector 1 2 is from origin to the xy coordinate 1 2 and the z coordinate 0. So initially we have 1 2 0. Now if we have to place this vector 1 2 0 to point 1 1 1, we have to move it parallelly and we have to lift it upward. So every vector is exactly the same. There is no difference. That is why we are getting this to be just a collection of vectors which are distributed quite smoothly. So the single vector, one single vector that is lifted upward. So for every value of see here what's happening is if you choose x and y, you will get one vector. That x and y you have to place at every height. So corresponding to that particular x and y, you will lift that vector upward and you will keep on lifting that vector upward. Corresponding to other x and y, you will be getting another vector. That vector you will lift upward from the xy plane and you will place it at every xy. So you are getting such a uniform distribution of vectors here, because the third coordinate is not about there. This is how we find the curl of a vector field. Now, to find the gradient also, a gradient we have already seen, not gradient, we have seen divergence. So to find the gradient, there is a gradient command already available. If you want to find the gradient, that also can be done directly. So f dot gradient. Oh, what happened to that? F has no attribute. Why is it happening like that?
For gradient, f should be scalar. No?
Oh, this is the vector variable function I have given. Okay, f has to be. So I define it as a vector, right? Oh, that's the mistake I did. Okay, sorry. So I need to redefine it probably then. I can redefine this as okay. Let me just define f of xy is a only, right? So three variable thing, right? F of xy is equal to, suppose I define it to be equal to sin x plus cos y plus this plus sine. So the gradient is turning out to be this. So if you have f as a scalar function, you will get the gradient to be equal to f dot gradient is the command that you can use, and you will get it as a vector here. So this is how we find the gradient of a vector value function. So the curl, now we have found the gradient is there. For finding curl, you can straight away use the curl command. For finding gradient, we can use the gradient command. There is nothing special about that. Now what is next available here? So what we have done is, what is the other thing? So we have plotted all these things. Okay. Characteristic polynomial, we have already done rank. the vector field. So integrating and differentiating vector valued functions, I already told that the integration of the vector valued function can be done the same way as in the case of the differentiation. So if you want to integrate the vector valued function, suppose that we define R to be equal to a vector. See, there is one difference. If you define a vector, if you define something as a vector, or if you write something as a tuple without using the vector command, the differentiation and integration kind of things cannot be performed on a tuple. So if you want to differentiate or integrate, you need to define it explicitly as a vector. So define R to be equal to t t square t cube. Suppose we define it like that. Integrate R with respect to t. We get the answer to be equal to 1 by 2